Okay, just a quick review of what we did yesterday. I failed to record this, so I'm just going to go over it really quickly. Section 3.4 is called velocity and other. I want to talk about the velocity thing for just a minute. S of t. S is what you're going to use in physics all the time for position. So this is position. It's also reference. It's good for distance. Anything. When you want to know where the thing is, this is what you use. And t is time, and it's usually measured in seconds. And if you're measuring things on this Earth in feet, the formula is negative 16 t squared. Negative because gravity pulls down. Plus v naught t. This is the initial velocity. If the initial velocity is also downward, then this is a negative number. Usually people throw things, well, they don't throw up, but they throw things upward, usually, like when you're launching a baseball. But sometimes people hit things downward, like when you're trying to hit a volleyball. And this last one out here is a constant. It is this S and this S, both mean position. This is the initial position. This is the initial velocity. Okay? Now, if you want to know how quickly position is changing, that's a rate. And that's a derivative. But if you want to know how quickly position is changing, you're talking about speed, sort of. If we call it velocity instead, now we can talk about a vector. And vectors have direction, which means they also have signs. Speed is just positive number. Velocity is a signed number depending on which direction it's going. And it's equal to, its velocity is the rate at which position is changing. And so it's the derivative of this, which is negative 32t plus v naught, since that derivative is 0. And if you want to know how quickly velocity is changing, you derive that. That would be the second derivative of position. We call that acceleration. And in this case, when you're launching things, projectiles on this Earth, acceleration is always negative 32 feet per second per second. So this is measured in feet per second. This is measured in feet. And this is measured in feet per second. Per second, which is feet per second squared.
Matthew Taylor, Connor Jensen, and Meg Fillmore, please come to the office.
Okay, so that's what all those things are. Acceleration is always constant if you're talking about projectile. And by the way, all of these things refer to strictly to the vertical motion of a projectile. It may also be going horizontally, but that is not what this is referencing. This references only the vertical part of the motion that goes up and back down. Okay, so that's a quick explanation of velocity. The author goes into much greater detail, which I think is silly. We did example 1 having to do with circles. If you're viewing this video, read that. If you have any questions, ask me about it. We also took a look, sort of in a loose way, the exploration 1 having to do with tree growth and how the rings get smaller and smaller as they go out. You want to study that. It's not very hard, but if you have any questions about it, let me know. And we got clear over to the bottom of page 129. That's where we are. So I'm not going to be on screen. I'm not going to put anything on the board unless necessary. You're just going to hear my voice. I need you to be paying attention to the picture. In the lower left corner of page 129, it belongs to example 3. So get there, and you're not going to see anything. You're just going to hear it. You need to be looking at the picture. Okay, so here's the scenario. You're looking at that graph down there. It looks like it came from a graphing calculator. It did. A student walks around in front of a motion detector that records her velocity at 1-second intervals for 36 seconds, and then obviously connects the dots with a nice smooth curve there. And so for 36 seconds, if you look at that, 36 seconds is a time, and time, as we see from things that move around, time is the independent variable, which means it's on the x-axis. And so if you count those tick marks, each of those tick marks is counted by 4s. So we got 4, 8, 12, 16, so forth, all the way up to 36. She stores the data in her graphing calculator and uses it to generate the time versus velocity, or the time velocity graph. So if time is the independent variable on the x-axis, then velocity is the y-axis. And that can take a bit of thinking for you to understand what you're actually looking at here. This people are very, very used to looking at a distance graph. So that they look at the graph and they go, okay, Y value, if it represents distance, means that's how far away from the motion detector she is. That is not what we're looking at. This is a graph of how fast she's moving and in which direction. Get it straight in your head. The Y values are velocity. That's how fast she's going, okay? And our task for this example is to describe her motion as a function of time by reading the velocity graph. We've got to look at that and understand what we're seeing. And the question asks, one of the questions we have to ask at the end after we describe her motion is, when is her speed a maximum? Now, yesterday we talked about speed a lot. I'm sorry if you're viewing this video and you missed that, but speed is always a positive number. It is not a vector, and it is the absolute value of velocity as you see just above example 3. So when they ask you what's the speed, they're trying to get you to understand that thing in the 10 box right there. So velocity can be signed, speed is always positive, or 0 at the very smallest. Okay, so if you're looking at that velocity graph, what I want to know is what's going on at 4 seconds. What has happened between 0 and 4 seconds? She has sped up. In those 4 seconds, she sped up to, and we didn't get, if you'll read very carefully, we were doing this yesterday as the bell rang, we have no idea what velocity is measured in. But let's pretend it's feet per second, okay? So that we can talk about it. Can you tell me in terms of numbers, if we go feet per second, and each one of the tick marks on the y-axis is 1. Look at those tick marks. There's 7.5 of them above, 7.5 below. And you notice below on the graph it says that it's a -4 to 36 by -7.5 to 7.5. So the tick marks on the y-axis represent 1 unit. So now that we've got all that established in our minds, between 0 and 4 seconds, what did she do?
She's at 4 or so feet per second.
You want to use the word accelerated?
Meters per second.
Feet.
Feet. No.
Feet.
Not that fast. I'm scared.
So you want to use the word accelerated there in the first 4 seconds?
Yeah.
I want to know why you want to use acceleration, because it's something that's instinctive to you, or because there's something about the graph and what we've discussed about acceleration that makes you want to use that word.
Because she's going faster. So that's acceleration, so it makes it sound fun.
Okay. All right. So she's speeding up, and that's an acceleration. That's a change in the rate of velocity. Okay. Now, she's speeding up in the first 4 seconds. In which direction? Positive direction. If we agree that positive is right and negative is left, and we're looking at the front of this room, then she's going that way.
And the motion detector's right there.
Yeah, the zero, yeah, no, the motion
Speed detector.
the motion detector is near the door.
And she's moving. Motion detector is moving positive along the x-axis, and it's measuring her speed as she travels.
Yes. So what I want to know is, what does that 0.00 right at the very beginning? That means 0 time has elapsed, and she's also moving 0 feet per second. Where is she at that point?
Right next to it.
Why do you think that? Why do you think she's right next to the motion detector then?
Because it's not. Oh my goodness. Because I was thinking about distance.
Yeah, and don't get stuck in that trap.
Oh.
Where,
Long.
listen, where is she when we start the clock on this project?
Around in front.
In front of the motion detector is all we can determine, because there is no beginning speed or no beginning position here when we're talking about velocity. That's an arbitrary thing that no one can tell from this graph. Don't sucker for this being a position curve. It is not. Don't let your mind switch on you. And Connor, you did that perfectly. That's what I was hoping would happen, and thank you for that, but don't do it again. Okay, so.
It was the perfect mistake. That's what I'm
Okay, so where is she? That's not a question we can answer from this graph. Where is she when we start in front of the motion detector? That's all we know. So she might be here, but there's nothing in the graph to indicate that. All we know is that when whoever's doing this clicks the button to start recording is when she starts moving this way. But we don't know where she starts from. Y'all clear? Okay, be careful what you can tell and what you can't from this thing. Okay, so All we know for sure is that she started with 0 velocity, and immediately upon starting the clock, she began to move and was speeding up. What happened first or in between 4 and 8 seconds?
She stays the same rate.
Is she still moving?
Yeah, she's still moving, but she just thinks.
Right, she's not speeding up or slowing down. She's still moving in which direction? Forward. So this is going to be kind of funny, and there's not nearly enough room. So at the right at the beginning of the clock, she starts to speed up like this, and then she stays for the next 4 seconds, but still moving forward. You follow? Okay, all right. What happens in the next 4 seconds between 8 and 12? Well, probably more like between 8 and 14 if you really look at it. She's doing what? Slowing down and moving forward.
Her choice to move in that direction.
How do you know she's still moving forward before she reaches 14 seconds? Yeah, good. Okay, so what happens at 14?
She turns around and she forgot to start.
She may not turn around, but she does for how long?
Just a little bit.
Just an instant. Just an instant, and then begins to.
Go back down to its rate.
And what is she doing between about 14 seconds and say, let's see, that would be 16, 20, just about 21 seconds. What's happening there?
She's like sprinting.
She's sprinting?
Reverse. She gets to the point where she really needs
If you say she's sprinting, which direction is she sprinting?
back towards it.
And so when you say she's sprinting, tell me what's happening between 14 seconds and about 21 seconds. In which direction?
Backwards.
Towards the motion detector, maybe?
Yeah.
What happens at about 21 seconds then?
She starts coming back down. So she's getting back down.
She's slowing down? Which direction is she moving?
Still moving back there.
Still that direction. Still backwards. Until about, let's see, that was 20, 24, about 26. What does she do at 26 seconds?
She stops.
Stops. Completely stops because velocity is 0. For how long?
She forgot what she 6 seconds.
About 6 seconds, and then she starts up again. So the motion went something like this. She started somewhere in front of the motion detector, and she sped up, and then she went the same rate, and then what'd she do? Slowed down, and then stopped, and then started going this way, sprinting, until, and then what'd she do? She slowed down. Did she stop?
Yeah.
Okay, and then she waited for a minute, taking a breather, and then
Start going.
forward again, and faster, and then we lose track. Right?
Yes.
Okay. What is her maximum speed?
7 per second. See, yes, absolute velocity, velocity.
It's when she's farthest from the x-axis. That's when she's moving fastest, and it doesn't matter which direction because speed doesn't reference sign. And the farthest distance occurs at around 21 seconds as opposed to the other one, which occurs at around 4. She's going faster. Does that make good sense? Moving on. All right, let's take a look at example 4. In the free fall constants, they're talking about that in that box right there. By the way, they tell you that acceleration is the second derivative of position, which is the derivative of velocity, which I already have on the board. Okay, free fall constants. We already discussed that yesterday too. If you missed that on the tape, I'm sorry about that, but it's actually 32. And this first term right here in the position function is actually 1/2 gt squared. And g is negative. That's where the negative comes from, because gravity pulls down, and thank goodness. Can you imagine at 2 o'clock every day if gravity were reversed? Can you imagine how our lives would be different?
Here's the next question. AM or PM?
PM.
For both.
PM. I'm not doing that. Yeah, tie yourself to the bed. Yeah, that's what they have to do, and that's what they have to do in orbiters. You have to kind of be tied down a little to sleep. Slow down.
I could not get you. So you have to like staple your bed there.
Okay, so anyway, that's where the negative 16 comes from. The force, or not the force, the acceleration due to gravity is actually 32 on Earth, if you're talking feet. Here's what's really cool about using meters on this Earth. 9.8 is really, really close to 10. And so when you're in physics and they're measuring things in meters, you can do your calculations and get a really good estimate just in your head, because it's practically 10. It's cool. Anyway, not so with the 32 feet, because that's an arbitrary thing. All right, anyway, here we go. Example 4. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second,
Oh, shoot.
which is about 109 miles an hour.
That's cruising.
Yeah, that's cruising. It reaches a height of, and notice how they put this. They don't say S of t, but it is S. S equals 160t minus 16t squared. So they've got the terms backwards, but they've got what we need. If you'll take a look, it projected it upwards, so 160 is positive. This is always negative. They reverse those two terms, and the initial position was ground level, so it's 0. You see all the pieces there? Okay, all right. And it says after t second, oh yeah, that's the equation. And if you plug a t in, it'll tell you how high it is. So we got to answer these questions, and these are classic questions for an exam, including a final exam or an AP exam. These kinds of things, they love to ask you this stuff. So that tells you that this is stuff that you should keep in your mind for as long as you're studying stuff or working in an industry that requires you to project things. Yes, dynamite. One thing up. Okay, so the first question is, how high does the rock go? Yeah, not a good answer. How high does the rock go? Are we asking a velocity question, an acceleration question, a position question? What are we asking? Position. How are we going to answer that question? We're not going to use your calculator. We're not using your calculator. I know, and you can later. But for now, no. You have to think conceptually. What's that? Find the vertex of the position equation. Yeah, that would be great. We could do that, and the y value would be the answer, right? So that's one way we could do it, and we have the skills and the means to do that from algebra and pre-algebra calculus. What?
Can we derive it and then find the horizontal tangent? Would that be the best way to do it?
You're thinking along the right lines. So we could find, you're right, we could find the vertex, but that doesn't require calculus. So that's good thinking. I'd really rather do this with calculus since that's the name of our course. Okay? And position, you said, they said was 160t minus 16t squared. Shh. And we know this thing's going to be a parabola which opens downward because that's negative. And it's going to start, the time that we start on this thing is going to be right here. So its position is right here. And if we graph this position curve, keep in mind, this is an S of t curve, not a V curve like we had just a few minutes ago. Okay, turn this just a smidge. Okay, so it's going to start right here. And if this is time, the rock's going to go right straight up and down. This is not graphing where the rock is. It's graphing how its vertical position goes along. So we actually get a parabola. Because time elapses as the thing's going up and down. What?
That is a good parabola.
Yeah, I've been doing this a while. Okay. Anyway, so we are looking for this value right here to answer how high does the rock go. And you said we could find the vertex. I don't want to do that. You could, and you did that on a test, and you did it that way, and I saw your work. It would be fine. All the tools you've established up to this point are great, but I want to do it with calculus. And you mentioned something about this tangent line right here. Because all the other tangent lines that we would draw have a slope of something, right? But that particular tangent line right at the vertex has a slope of 0. So what I'm suggesting is that we find the derivative and set it equal to 0. Because when the slope, which is what a derivative is 0, at that time, at that t value, the rock will be right here. Then what do? Plug that t value into the position curve to find out where it is vertically. It's vertical position. Does that make good sense? So the main thing that you got to realize is that when you're looking for where something is, especially when it's changing direction, you want to look at when the velocity is 0 because that's how high it goes. It stops for just an instant. And then wherever it is right then, it starts coming back down. Do you understand the concept? Okay. So if we set this equal to 0, we get 160 equals 32t. Divide, you get 5. Trust me. So this is 5. But that still doesn't answer the question, but we now know what t-value to plug into position. We want to find s of 5. And that's going to be 160 times 5 minus 16 times 25.
We use our calculators now.
I guess.
No.
16 times 25 is 400. 160 times 5 is 800. And 800 minus 400 is 400. So the answer to that first question right here is 400 feet. And it is feet because this is measured in feet per second.
How high it is, right?
How high did it go? Maximum height.
I did that one falling on.
We okay with that? Okay. Next question. So we used calculus to do this, and that's kind of what I'm hoping you will do. What's the velocity and the speed of the rock when it is 256 feet above the ground on the way up and on the way down? It reached 400, so it's going to hit 256 twice.
The velocity and speed of the rock, is there any difference?
Absolutely.
Velocity is positive going up, negative coming down, speed is the same in either direction at 256. So this is 400, 256 is around right here. And I think you understand it's going right here. However much time has elapsed there, that's how it's going to be going, or it's going to be at 256. It'll also be at 256 over here.
Oh, so we're on that goal. Yeah.
We're trying to find its velocity, which means we've got to have something to plug into here. We got to find its velocity, and we've got to find its speed. But that's going to be an easy thing. If we find its velocity.
So we start with the position.
I'm gonna erase this stuff here. What did you say?
Start with the position.
Why? Because we're asking a velocity question. We need to be able to use this equation, right? But we need a t-value. But what they gave us was a position value. So you're right. We start with position this time. Do you understand that?
Find the t-value.
You following?
and then
Everybody
we
following?
to-
They're asking you a question about this, but they gave you information about this. We have to make them work together again, just exactly as you said. So we want to find S. No, we want to find when the position, we want to know when that is 256. We want to know the t-value. Since that's a quadratic, and we prefer to handle quadratics when the leading term is positive, I'm bringing these guys over here. Okay, 256 minus 160 is?
T, there's a T on the 160.
What?
It's supposed to be
What's
T on
160?
160 T.
This is position 1.
Oh, yeah. Right.
Boom.
Yeah.
Boom.
Okay.
Boom.
That's what I want to solve. I need to find the t-value for that, right? Do you understand in the physics of this why we're going to get two values? We always get two values with quadratics that cross the x-axis. You understand what those two t-values will be? That one? And that one. Okay.
I understand.
All right. So do we want to try to factor this?
Yeah.
Okay. 16 comes out. We have a t squared minus 10t plus 16. Do you know of any factors of 16 that add up to 10?
Yeah.
16 can be ignored, so I'm not going to write it down. I'm going to write this down, right? So t is 8 and 2. Here's the 8. Here's the 2.
That looks pretty perfect.
Yeah, it was well designed. Whoever wrote this problem, it was good.
That is sense.
It took a little effort to try to get it just right. Okay, so we now know the t values. To find the velocity at those times, we plug them in here.
Oh, dang. I like it. What the heck?
So first one I want to find is v of 2, because that's what happened first. That's just what I want to do first. So I want to find v of 2, and that's going to be 160 minus 64. Do you agree?
Yeah.
And that is 96. Now I want to find v of 8. Oh, by the way, what's the units on this? It is not.
Second.
Yeah.
Feet.
V of 8 is going to be 160 minus
224.
224, is it? 224. If you subtract those, you get, is that right? It's not 224.
1, 2, yeah, 256. Dang it, Sam.
How much?
256.
256. And what happens when you subtract those? Without doing it on your calculator, what do you expect?
96.
Negative. 96, people. So its velocity is 96 feet per second on the way up at 256. Its velocity is negative 96 feet per second at 8 seconds on its way back down, and its speed at either one of those locations is 96. Huh? Feet per second. Yep.
Meters per second.
Next question. Here's the question C. What's the acceleration of the rock at any time t during the flight?
Why is the acceleration of the rock?
32. Negative 32.
Negative 32. No matter where in its flight it is, its acceleration is always negative 32.
Isn't it just anything is the acceleration is always negative 32?
If you're talking projectiles, absolutely. And measuring things in feet, yes.
Cool.
Yeah.
So acceleration only refers to velocity, not speed.
Acceleration refers
To acceleration.
to the size of the force of the accelerator, which is gravity.
But acceleration refers to velocity, not speed, because if it referred to speed, then your speed would.
Right.
obviously
Yes.
be-
Acceleration is a vector and refers to velocity. Yes. 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 Yes.
Negative 32 would not work as our accelerator.
If you're on acceleration.
What? If you have a spring, if you have a spring, for example, especially if a spring that oscillates up and down like this is bouncing, then you've got, because that spring is constantly changing acceleration, because at one time it's being compressed, the other time it's pulling, and it's just, you know, and so you get a different acceleration when you're talking about that. When you're talking about projectiles, the only accelerator is gravity. Okay, and it's in free fall as soon as you let it go, even though it's going up. It's in free fall all the time, even though it goes up. It's weird. It's hard to get used to. Okay, and the last question is, when does the rock hit the ground?
Yeah, it's not zero.
When is a time question, right? When does the rock hit the ground?
Gotta be 10 seconds.
It has to be 10 seconds because of the symmetry of parabolas.
Oh, yep. Awesome.
How could we do that with an equation and not conceptually thinking? How could we figure that out?
Yeah.
Yeah, set position equal to 0. Exactly. Put a 0 here and solve this quadratic. And you will get 0 for one of the t's. That's this one. And you will get 10 for the other one.
That's not.
Okay? All right. Take a look at example 5. Studying particle motion. Okay, we're going to do another problem. We're going to answer a lot of questions about it. But this time, a particle moves along a line, so the particle is now moving horizontally, which means we are not restricted to that parabola for our position equation. If we're moving horizontally along a line, gravity is no longer an element. Gravity is constantly pulling down at it anywhere it is, so it's irrelevant. That didn't make a lot of sense, but we're going, the motion is horizontal, which means this vertical stuff doesn't apply. Okay? They love these problems on tests. These particles moving along a horizontal line. It's not reality at all. It has to be lots and lots of stuff. So just use your imagination. A particle moves along a line so that it's positioned at any time when t is greater than or equal to 0. You need to pay attention to that because sometimes when you do the math, values for t turn out to be negative. You are to ignore those because of this stipulation right here. And if you put them down because you weren't thinking about it, it will cost you. This is good for only time greater than or equal to 0, as you might imagine. Time moves forward, not backwards. Is given by the function t squared minus 4t plus 3. So we're dealing with another quadratic, but it's not this one. Where s is measured in meters and t is measured in seconds. These are the things we are to ask ourselves. What is the displacement of the particle during the first 2 seconds? That's a loaded question, folks. We haven't talked about displacement yet. I'm going to talk to you about that concept. Displacement, listen carefully to this and see if you can start to fit things together in your mind. Listen. Displacement is to distance as velocity is to speed. Displacement is a vector, people. It has a sign value to it, displacement. Here's what happens. If we're going to, and I have to draw it this way so that you can see what I'm talking about, but if this is the particle moving along this line, let's say it starts here, I don't know, some arbitrary place. And we start the clock right here, and here's the position, and right at the time we start the clock, the particle is moving forward. And then at some point, it turns around and comes back here a ways, maybe even back here, and then it turns around and we stop the clock right there. What is its displacement?
0.
0. Because it's in exactly the same position it started from. So how far has it been displaced from where it started? It hasn't been displaced from that position at all during the time we clocked it. And yet, it went a long ways. Its distance is not 0, but the displacement is. What?
So it's basically just like the, like absolute value of like where it started to where it ended up.
Not exactly. Yeah, well, yes. No, well, no, it isn't. It isn't absolute value. Displacement can be signed.
It can.
Oh, yeah. So if I make this a number like 4, it started at 4, it landed at 4, it has not gone, it hasn't been displaced from that position. Okay? If instead, though, I stop the clock right here, what is its displacement?
4.
Not 4, negative 4. Because it landed to the left of where it started. So this displacement is negative 4.
N minus.
Yes, end minus beginning. Exactly. End position minus beginning position. Okay? So we say displacement is equal to position, which we use for S final minus S initial. That is displacement. So if I was to continue this thing instead, we let this thing go a little bit farther, up to here, and I say that this is 10, then what is the displacement? 6. 10 minus 4. Okay? It's 6 units farther to the right than where it started. That's what you're asking. What's the displacement? The distance is much greater than 6. Do you understand that?
Yes.
Okay, and displacement is a vector. It can have a sign depending on whether you landed to the left or to the right of the initial position. So when we talk about displacement, it says, find the displacement of the particle during the first 2 seconds. Let me tell you, folks, the biggest mistake that's made here, and it's made by the smartest students I've ever had, not always just them. People make this mistake all the time. Shh. People always their assumption is that all particles start at 0. That is very seldom the case. That's what they think. So when they answer a question, find the displacement of a particle during the first 2 seconds, they plug a 2 into the position equation, and that's how they answer it.
Oh, no.
All you have found by plugging 2 in is this. You have to plug 0 in to find this. And the answer isn't always 0, as in this case right here. The initial position of this thing when we start the clock is 3. Can you see that? You see why that is?
Yeah.
So the initial position is 3. Final position after 2 seconds is going to be 4 minus 8 plus 3. Yeah? What's 4 minus 8 plus 3?
Wait. 4 minus 8. Yeah, negative 1.
4 minus 8
Yeah, negative 1.
plus 3, negative 1. So its position after 2 seconds is negative 1. What's its displacement? Negative 4. Look, this final one comes from plugging the 2 in, and we got negative 1 for that. This initial one comes 0 in, and we had 3 for that. Besides that, it started here and landed here. Where did it land from where it started? 4 units to the left. Its displacement is negative 4, whether you think of it on a number line or whether you remember this formula. But don't forget to calculate this as well. That's the biggest mistake. Everybody assumes all things start at 0. They don't. Most of the time they don't. You mess it up, so be careful. Sometimes it does. All right. Now B says, now this is very, very important that you read math slowly, especially right here. It says, find the average velocity of the particle during the first 4 seconds. What should we do?
Find the velocity of the beginning and the end and average them.
Nice try, but no.
I'll take nice try.
That's what most people would do. Actually, most people in calculus would run right over that word average. and they would find, what they would do is they would find the derivative of the position function, plug a 4 in, and answer with that. That is wrong. Because that's instantaneous for us. We want average. Do not gloss over the word average, ever.
Never mind. Speak. I don't know how you do it.
You know how you do
Use
that?
the derivative and then do find the 2 points and average them out.
No. That's what he suggested we do. Is find the velocity, beginning velocity, and average velocity. Do you remember one of our very first discussions we had in this class was, if you want to know your average speed going to Idaho Falls and back, you can't just average the velocities going and coming because you spend more time going slow.
Yeah.
How do you find average velocity?
How do we find average?
Total distance over total time. How do you find total distance?
Displacement.
Is it displacement?
Yes,
Remember,
it's
distance can be a lot more than displacement. However, Jose, you are correct. Displacement is what you use.
Why?
Well, how do you know if you can use displacement and it doesn't look like that? If the
If it moves around like that, because we only care well, actually, hang on a second here.
Oh no.
It's important that you get this down pretty well. So you take the, to find the average velocity, you have to find distance, right? Total distance divided by total.
Yeah.
It is actually going to be displacement. You have to find the position at 0, or the position at 4 seconds and the position at 1 second to find out how far was displaced. Because this distance counters this distance.
Oh.
They undo each other.
But if we were doing speed, it would be.
Right, now listen, this distance from here to here and this distance from here to here undo each other because they're opposite in sign. So really, the only distance we're considering is from here to here, because that's the only chunk of this line that doesn't get countered by somebody else with a sign. You know what I'm saying? So it is displacement. So we found displacement here was -4. In other words, SF, well, no, actually, that was when it was 2. We have to find S of 4 minus S of 0. That would be total displacement. Yeah or not? Total displacement. That means distance from the beginning, where we're not accounting for all of this other motion that got positive and negative out. Okay? Over total time. How much time has elapsed for this question? 4 seconds. So we take final time minus initial time. The reason why it's important to write it like that is because what if it had said, what's the average velocity from the second to the 4th second? Then this would be 4 minus 2. But it says for the first 4 seconds, which means we're considering it starting at 0. So it's still important that you take final time minus initial time. Okay, so this is what we would do for this particular problem. What?
is S of 0 mean the position at 0 seconds?
Yes.
All right. I think that's good.
These things we're plugging in are time values. So if you want the first 4 seconds, then this has to be S of 0, and it's not always 0. Speak.
Will we ever learn how to figure out the speed?
The what?
The average speed. Like if we had something like that.
Sure. Yeah, we could.
Parabola. You could find the distance that parabola travels.
After Christmas, when we start studying integral calculus.
Your present.
That's pretty intuitive, Sam, but we're not going to tackle that yet. But yes, we will, and that was a good question, but you're going to have to hold off on it. Okay, so this is for this particular problem. I want to write this on the board, so maybe you can put it in your notes. Velocity average, with the notation we've been using, is S, I'm just going to write it with subscripts, S final minus S initial over time final minus time initial. And this isn't always 0, but it is in our case for right now. This is how you find average velocity. Position at the final time, position at the initial time over how much time has elapsed for the problem. So what was S of 4? Oh, I guess we need a function. Let me put the function up here. S of t was, can somebody read it to me? T squared, was it?
Yeah, 3 minus 4t.
Plus 3? Okay. So what was S of 4? 16 minus 16 plus 3? 3. Okay. What's S of 0? Oh. What was the average velocity? That's 0. Because it might have done something like this. This velocity and this velocity add up to 0. This velocity and this velocity add up to 0. Right, you're right. So it would have just done this and this would stop right there after 4 seconds. But the average velocity is 0 because it spent the same amount of time with a positive velocity, same velocity, and the same amount of time coming back. Average velocity is 0. Okay. Average velocity, it has to do with position, people. Make sure you remember that. Okay, moving along, getting a little bit more done here. C part. Find the instantaneous velocity of the particle when t is 4.
This is where you can do derivative.
Yeah,
Now
we can do a derivative. So what is, I'm coming down here. So what is S prime of t? 2t minus 4, and we wish to find, that's velocity, so I'm going to call it that, v of 4, which is, yeah, it's 8 minus 4 equals 4. So it is moving forward at this point. So it didn't do this. It went back and came forward that way. That's what happened. If we want an accurate graph of this particular particle, it went backwards and then came forwards because it started at 4. It went back a ways, came right to there. We know that that average velocity was 0. But we also know that when time is, I'm sorry. I can't do the velocity. This is not a velocity curve. This is a position curve. Never mind. But it is moving forward at 4 feet per second, or whatever the units are. It's moving forward because it's positive. So the instantaneous velocity at 4 seconds is 4 units per second. Yeah.
So why is the graph just weird? Why is it only on that?
Because the particle is moving along this line. This is what the particle is actually doing. It's starting here, and it goes out of your ways, and it comes back. And you can't see that unless I separate it a little. So this isn't.
Okay, but I thought it was like a quadratic, so how?
It moved, its position is quadratic, it goes back, it's its vertex.
So you wouldn't actually graph like quadratic either,
It's just,
okay, that's cool.
If you were graphing the position curve where position was on the y-axis, it would look like this. Well, it would hit this. It would have a position that is going backwards, diminishing. This is position. It would go backwards until it reached a point where it turned around, and then it would go forward. Okay, wait just a second. This is an arbitrary place right here. It could be here, it could be down here. All I'm saying is, as it turns out, because we know it reached -1 at some point, it's actually more like that. Okay, but it's going to move backwards and then forwards.
Okay.
That's what that parabola tells us. And it's going to start positive and open upward because we know what about parabolas, and that leading coefficient is positive. So we know it's going to be shaped like this if this is a distance curve. Okay?
Got it.
All right. It's hard to reconcile all this stuff, but you'll get used to it because you can see a lot of it. Okay? Next question. Find the acceleration of the particle when t is 4. What's a of t, first of all? That would be v prime of t. Look up here. So what is the acceleration of 4? 2. What's the acceleration at 3? What's the acceleration at 100,000?
It's 2.
Right. Can you see that the acceleration would have different values if the initial function were cubed?
Yeah.
Because then this would have a t in it, which means the acceleration would change. Okay? It's even worse, and you'll see it later, it's even worse when we let the initial function be 3 sine t. That'll be fun. You'll get it done. And it'll be enlightening. Just hang in there. Don't enlightening. Okay. All right, so E says, describe the motion of the particle. At what values of t does the particle change directions?
What was that?
Can you describe the particle without answering that last question? You can, but it is a complete description. We actually described it right here. Can you describe what the particle's doing for the first 4 seconds? Right when we start the clock, which way is it going? Going left? How do you know? Because velocity there at t equals 0 is negative. That's how you know.
Oh.
It's going left, and then after a while it turns around and goes right forever.
Yes.
This thing's going to keep going like that, right? But start the time there. Remember, t greater than or equals 0? So it goes left, and then it goes right. And then the question asks, how far left does it go before it turns around and goes right? How do you know it's -1? Just because that's what's on the graph?
No, because.
And if so, then I haven't drawn this correctly. And I'll fix it if I need to.
The position one.
Is it the position one?
Yeah.
I don't think so.
What?
Think about the rock that we just fired upward with the dynamite. How did we figure out how high it went? That's the same question. How far left did it go? Yeah, when the velocity is 0. When the velocity reaches 0, the thing's turning around. It has to stop for an instant, right? When is velocity, which is the derivative of position, when is this equal to 0?
At 2. 2.
At t equals 2. And what is the position then?
4 minus 8. -4 plus 3.
-1. We did that already when we did displacement, remember? Okay. So this is incorrect. It does turn around here. And this is more correct now if this is -1. Yeah? 2 different graphs and different ways of looking at it. Okay? And so a better way to describe it is when we start the clock, its position is, what's its position when we start the clock? Is it?
It's 3.
Yeah, it's 3. So it starts at 3, moves left 4 units in the first 2 seconds, turns around and goes right forever. That would be a description of its motion. It tells you how long things are and how much time it took and exactly where it started and turned around and everything. Do you understand how to answer all those questions? Because you will be asked these questions these same 5 questions over and over and over. You need to be able to find them. We're not doing F because we're not studying parametric graphing. So F is out. Okay, I am jumping clear over to example 6. I have notes to myself on both these explorations. Don't do it unless there's time. We're not sure there's time. We're not sure how enlightening they are. They're not that great. However, example 6 is pretty cool. This is an example of a problem using calculus that does not have time as the independent variable. Y'all remember Gregor Mendel? What did he do? He grew peas in many different generations and studied them for genetics and hybridization, stuff like that, right? We did the little Punnett squares and all that stuff in genetics. Okay? So he says, working with garden peas and other plants provided the first scientific explanation of hybridization. His careful records showed that if P, now listen carefully, you got to get this in your head to understand this problem, that P, which is a number between 0 and 1, because P stands for probability, it's always some decimal, Like, for example, the probability of rolling a 6 on a 6-sided dice is 0.17, 0.167, because it's a sixth. And so that decimal p is between 0 and 1. Okay? It's the relative frequency or probability of the gene for smooth skin in peas. And it's dominant. Smooth skin is dominant, remember. Then that means that 1 minus that frequency, or 1 minus that probability, is the relative frequency for a gene of wrinkled skin, which is recessive. Does that make sense to you?
Yeah.
Okay. Then the proportion, and you don't have to understand where this comes from. Then the proportion of smooth skin peas in the next generation will be 2p minus p squared. You do not need to understand why that is. Just understand it's a parabola that opens downward. Okay? And remember what p is. P is the frequency or the proportion in the first generation of the dominant gene. You with me or not? So if you start out with a whole bunch of smooth skin peas, so that the proportion or the fraction of all the total, the proportion is 90%, then P would be 0.9. If 90% of your plants express smooth skin, could be that some of them are hybrids, but the dominant gene gets passed on, right? If it expresses and you see it, you can look at it and say, okay, of all these plants I've got here, 90% of these have got smooth skin. Then you've got a population of, in your first generation, of a lot of dominant genes, right? However, if you've only got 10% dominant, all the rest are wrinkled, you can be sure that the wrinkled ones have 2 recessive genes, right? Because that's the only way it expresses that. Okay? So you got, let's say the proportion was only 0.1, that's what P is, then let's see what's going to happen. If you believe, and you should, believe that parabola is true, then look at the blue graph to the left of example 6. And along the x-axis is the proportion of smooth-skinned peas. What is the y-axis? Read your words again on the problem. What does the y-axis represent? It's in the last line of the equation, or of the question.
The wrinkled skin,
Nope.
the next generation.
Smooth skin in the next generation. The proportion of smooth skins in the next generation is what y represents. P is the fraction or the proportion of smooth skins that you start out with. The y values is the number of smooth skins in the next generation. So if you start out very, very close to 0 on the y-axis, on the x-axis, look at the blue graph. If you start close to 0 on the blue graph, that means you don't have very many dominant genes because P is small. That's the proportion of dominant genes. Are you with me? Smooth skin. If you have very few of those, then if you go up to the graph and over, your next generation won't have very many, but more than the first one did. Right? Okay. If you start out with a lot of smooth skin peas, so you're closer to the 1, and you go up to that graph, your next generation is going to have a lot of smooth skin peas, and it's going to be closer to the same number. So that if you start out with 100% smooth skin, your next generation is going to have 100% smooth skin. Yeah? But that's not what we're interested in. What we're interested in is how quickly the proportion of smooth skin is changing in the next generation. You catch the word? Changing. Okay? So if you start out with a whole bunch of smooth skin peas, the rate at which the number of smooth skins changes in the next generation is small or large? I know, you're still trying to get that in your mind. Let me say it again, I'll say it slower, try to get it in your mind, I'll say it slow. If you have a lot of smooth skin peas, a lot, dominant gene, and so quite a few of those, and we want to know how fast will the number of smooth skins change in the next generation. How fast is it changing if you start out with a lot? Will that number be small or large?
Yeah, the curve flattens out, so it looks like it would be smaller at least.
The curve flattens out. Excellent. This is a picture of the derivative. This is a measure of the rate of change. This one, right there, the red one. So you can read this graph if you understand what I'm asking. I'm asking about how things are changing. The derivative is this line over here that has a, well, let's see. Why is it sloping? Oh, the values are positive. You're right about the slope of the blue curve. Every time you draw a tangent line in that blue curve anywhere, it's got a positive value. But it's getting smaller and smaller and smaller and smaller until it becomes 0 at 1 because that's where the tangent line is 0, right? You following? And so the rate at which your smooth skins are changing, the closer you get to 1 with the first generation, is smaller and smaller and smaller until there's no change at all. Because if you start out with 100% smooth skin, you'll get 100% smooth skin and there is no change. But if you have very, very few smooth skins to start with, you will have a dramatic change in smooth skins in the next generation. Because those whole bunch of recessives that you had, they're going to share one of theirs, and it's very likely that the smooth skin expression is going to share, there's a 50-50 chance it'll share the dominant one. But the rate of growth in those expressing smooth skin is quite high when you have a very small number of dominant genes. Okay, the rate of change is high. Not the number but the rate at which it's changing. Did you follow any of that? Yes. It's kind of an interesting, quite interesting way of studying this stuff. And I think it's really cool that Gregor was a monk, and he understood this stuff. You know why? Because monks don't have to worry about where their next meal's coming from and go out there and scrounge it up. They get supported by the church and they have time to think. I'm talking about the old days when people were wondering where their next meal was coming from. Anyway, all right. Last thing. I think we got time to finish this. This is a case where, besides physics and projectile motion, this is another case where derivatives, the study of differentiable calculus, comes in really handy is with economics. Now, I need you to understand that fundamentally, people who have a passion for economics or really like to do that stuff generally don't have a passion for pure mathematics. I know, you're thinking, well, it is math. No, kind of. They have an interest in money. And they really don't care whether the money that they're going to make today is $130 or $140. They don't care. It's the size of those numbers. It doesn't matter to them. They just want to make sure that they're making money and that it's continuing to grow. And so they don't pay attention to the details of the number. A mathematician would say, but you started out with 130 and today you made $139.26. That's important. The economist will say, no, it's not. $140 is good enough for me. So pure mathematics and being precise is not an issue here. And that's why the calculus works for them. So listen. In a manufacturing operation, the cost of production, C of X, obviously, right, is a function of X, which is the number of units produced. So if you are producing calculators, then X is the number of those that you make. C of X is your cost that you have to output, you have to give out in order to get your raw materials, pay your employees, pay your taxes, all that kind of junk. And it's based upon or is dependent upon how many calculators you produce. Yeah? You with me? Okay. The marginal, this is the new word, the marginal cost of production is the rate of change. Ooh, rate of change. In our class, that means derivative. Marginal anything in economics is the rate at which the original function is changing. Marginal means derivative, get used to the words. So it is dc dx. Suppose C of x represents the dollars needed to produce X tons of steel in 1 week. It costs more to produce X plus H tons per week, and the cost difference divided by H is the average cost of producing each additional ton. Okay, I just wanted you to understand what marginal means. I don't really want to go through all of these definitions and going back to the definition of the derivative and all that kind of crap. I want you understand that marginal anything means derivative. Then let's look at example 7. Suppose it costs x cubed minus 6x squared plus 15x dollars to produce X radiators if you're producing 8 to 10 of them. And that the revenue, remember what revenue is?
How much money you bring in?
How much money you bring in. It has nothing to do with profit. Well, it does have something to do with it. Revenue minus cost is profit. Yeah? Okay. So R, that's what revenue is also a cubed function. X cubed minus 3x squared plus 12x gives the dollar revenue from selling X radiators. Your shop currently produces 10 radiators a day. Find the marginal cost and marginal revenue. What do we got to do? What do we got to do?
Find the derivative of both of those.
Find the derivative of both of those and do what with it? Three-syllable word, starts with E.
Endurance.
Next letter is V.
Execute.
Evaluate.
Evaluate at.
Evaluate, that's what
All right, fine. Evaluate at.
Eight to 10.
That's what it's asking. What are the marginals when X is 10? That's all you're asking. If you understand that marginal means derivative, even if you don't understand economics at all, you can do this problem. If you understand marginal means derivative. What is the marginal cost for this thing? Go ahead and give it to me. It's C prime of X. What's the marginal cost?
3x minus 12x.
3x squared minus what? Okay. What's R of X? R prime of X. Oh, I need a 15? Because that is an X term. Okay, what's this one? Marginal revenue.
3x minus 6x plus 12.
Plus what? Okay. So we need to evaluate this at 10. What is C prime of 10? Well, it's 300, right? Minus 120 plus 15. What is that?
295? No, 195.
265.
Why did I say that?
165.
195.
What's 300 minus 120? 180 plus 15? Yes, you are correct, 195. Okay. What is the marginal revenue when we sell 10 of them? 300 minus 60 plus 12. What is that?
2.
52.
1.
2.
52.
Oh my God.
Okay.
This is why I don't check on my calculator.
Anybody have any idea what this means? What these mean in the context of the economics? Knowing what you know about calculus.
How much it takes.
Those are the talking
The
about.
other one is how much you make. So for every $252.
That's what cost and revenue mean. I'm talking about the marginals.
That's like the change in, you know.
Give it a shot.
For every extra ton of, is it ton? No,
We're doing radiators now.
This is radiators.
Yeah, we switched to radiators, I know.
For every extra radiator you produce, you make $195 million. At 10.
That would be a revenue explanation. That's okay, but that's not correct.
So switch 195 50 52 and go at the bottom.
What?
If you did that, if you took this minus this, that would not be revenue. I mean, that would not be profit. It would be marginal profit. Based on what you know about calculus and this scenario, can you describe what that number 195 means? It is in dollars.
The cost.
not just the cost.
How much more it costs for each unit you produce?
At 10 units.
And then the other one is how much more you make.
No,
And so the
bring in.
difference is the profit.
Yeah, the change of the per moment, the marginal profit.
Okay, try again and try to be more clear. Use the words, use the number 195 and tell me what you believe it means.
It costs $195 more per extra unit you make to produce those units.
When X is 10.
When X is 10.
Because when X is 20, it won't be 195 anymore. So that's not a constant. It's not linear because this curve is not linear. It is roughly the cost of making the next radiator. Roughly.
It's like making it.
That's what I mean.
It's like that
Economists,
math problem.
economists don't care about the precision.
You know?
Let me show you what I mean, folks. Look, this is cool. This is a way of using a line to make an estimate for you, which is always easier to estimate with than a curve. If the cost curve, which the original cost curve was a cube function with a positive leading coefficient, means it's going to go like this, some way or another. So let's pretend it was like this, just for a second. And that this is 10 right here. And that this is 11 right here. This is the 11th radiator. This is number of radiators. This is cost. This is a cost equation, which means that C prime means the slope of the tangent line at 10. Right? That's the slope of the tangent line at 10. It's supposed to be 195. Obviously, this is not a correct graph. But at 10, right here, is the slope of the tangent line. Well, if you had that tangent line, can you see that the number on the tangent line, on the line itself, is awfully close to the number on the curve itself?
Yeah.
So evaluating the derivative, the slope, at 11 gives you roughly the cost of producing the next radiator. Now, if we were over here, then that cost would be, we'd have a steeper line, and that cost of, if this were 12 and we wanted to know the cost of the 13th, we would look at that line and it would be awfully close, but it wouldn't be 195.
Well, what happens if you're like on a sharp curve and you're near zero?
Well, then you got trouble. So you want to see the graph of it. You want somebody that knows math to analyze that for you because it can be significantly off. But most of the time, especially when you're dealing in production of thousands and thousands of items, if you're producing 3,000 items, that what this tells you is roughly the cost, very, very close to it when you get that number that big, the cost of producing the next item. Yes,
All we just use the C.
you could. You could be doing the same thing, but then you'd have to figure a slope where taking a derivative of polynomial is easier. Okay. This is roughly the revenue for selling the 11th radiator. Okay. So those marginals mean the approximate cost of making or selling the next item.
You got your revenue one up there.
It's very similar to that. This one.
Oh, really?
Yeah, very similar. Who comes up with these equations?
Not rich people.
Does anybody know what you call the person who actually studies what's going on in a company? And the demand and supply curves?
Actuary.
An actuary. They make good money. If you've got a mind for details and a mind for capitalism, that's an excellent place to go.
Nobody likes to work there though.
Excellent, excellent thing. So it's only four years of study. It's just a bachelor's degree, and you'll be making 6-digit right out the door.
Just a bachelor's degree.
Just a bachelor's.
Yeah, but it's an awful job.
Well, depends on who you are. Some people love
People only
it.
stay there for at most.
I had a kid go into actuary science, and he's making way more twice than I'll ever see.
I can do math all day, and as much as I like math, I don't want to do it all day.
You study the trends, and you study people. You study how people are thinking about different things, and you see the social, the society, the psychology of the history, and there's all kinds of stuff you study. But eventually, it does come down to numbers.
If
you have to come up with these, and you'd better be pretty darn close to right, because they make decisions based on what you come up with. Yeah, it's a lot of pressure. It is. Okay, that's the end of it. So 3-4 is assigned. Have a great time. Bye.